Alright, so in this video we are going to study two things. First, we are going to generalize the notion of a concavity and convexity to a multivariate function. And second, we are going to study the relation between this notion and the second of the conditions for optimization. So the notion of a concavity and convexity are very important in the study of economics. So if you continue to study economics in the future, you're going to encounter this notion several times. So we have to enhance the understanding about this notion. That is the main objective of this video. Okay. So we have seen this notion when we study optimization of a single variable function. So remember, a single variable function is concave if the second derivative is negative, and function is convex if the second derivative is positive. So its geometric interpretation is given straight line if the graph of the function is bent downward like this. So the slope of the tangent line is diminishing along this curve, so that is concave. So the second derivative is negative. For the convex function, the graph of a convex function is bent upward like this. Right? So the slope of the tangent line is now increasing. In other words, the derivative is second derivative is positive. Okay. So this definition and geometric interpretation is translated into three-dimensional space. So when we work with two-variable function, the function depends on two variables x and y, then the graph of this function becomes three-dimensional surface like this. Okay, but except that just the one difference, the concavity and convexity are easily generalized to three-dimensional space. So in case of a concave function, the graph looks like this upside down U shape. Yeah? But instead of this curve, we're going to have this surface, U-shaped surface. Okay? So that is one example of a concave function in case of two variable. This is one example of a convex function. Okay, so now we have U shape. So graph bent upward. So we have a valley in case of convex function, and we have a this kind of a hill in case of a concave function. Okay, but the thing is, how can I define concave and convex function if the function depends on more than two variables? Okay, then we can't visualize the graph of the function anymore. So we need some abstract or mathematical definition of a concave function or convex function. Okay? So that is what we are going to study in the next slide. So in the next slide, we have formal definition of a concavity. So in general, function f is said to be concave. So, the function f is defined on domain x, and we do not impose any restrictions on this x. So it can be anything. So it can be just a single variable, or say just x, or, it may depend on, so it may have, pair of elements, say x and y, or triple of elements x, y, z. Okay, does not matter. We can apply this same definition to every kind of function regardless of the dimension of the domain. Okay, so function f is said to be concave if for every pair of distinct points u and v in the domain, the following inequality is true. Okay, so we choose 2 points at random in the domain. Okay, so now in order to understand this inequality, we should be able to read this expression. Okay, so for this purpose, let me elaborate on the line segment for a second. Okay, so think about a one line segment on xy domain. Okay. say here we have one point at 1, 1. Let me call this point U, and one more point at 2, 2. Okay. And this point, let me call that point V. Okay. And think about the line segment joining these 2 points. Okay. And if you are asked, what is the equation of this line segment? Okay. Then you may attempt to answer, say, y equals x. Okay. But y equals x is another line segment. It is more like a straight line, right? It goes so the graph of this function does not stop at this point. It goes on forever. Okay, there is a no ending point and there is a no starting point. So it goes this way or the other way. It goes on forever. Okay. So what is the equation of the line segment? Okay, so for line segment, we have a parametric equation. Okay, so the way to write this line segment in math, using some parameter theta. That is a theta times the left-hand point, 1, 1, and 1 minus theta times the right-hand point, 2, 2. Okay, so here theta is some number between 0 and 1. Okay, now, in order to understand this expression, so this is called the parametric equation of the line segment. Parametric equation of the line segment. Line segment UV. Okay. So in order to understand this parametric equation, just let me put in 0 for theta. Okay. So remember, theta is any number between 0 and 1. Okay. So if theta is equal to 0, then this equation comes down to 2, 2. So that indicates the right endpoint. When theta is equal to 1, if you put in 1 for theta, you can easily check this equation boils down to 1, 1. That corresponds to the left-hand point of this line segment. When theta is 1/2, we have 1/2 times 1, 1 plus 1/2 times 2, 2. So we have 1.5 and 1.5, and that belongs to, so that corresponds to the midpoint of this line segment. Okay, so by adjusting the size of theta, you can essentially represent any point on this line segment. Say, if you're interested in the point dividing this line segment in the ratio of, say, 1 to 2, 1 to 2, then think about a theta as a uh, as a 2/3. Okay, so instead of 1/3, we have to put in 2/3 because this theta, the parameter theta, is the weight on the left-hand point. So that is the weight we put on the left-hand point, and 1 minus theta is the weight we put on the right-hand point. So when theta is equal to 2/3, okay, we are gonna have this point dividing this line segment in the ratio of 1 to 2. Okay. So just by adjusting the size of theta, you can represent any points on the line segment. So this is why this equation becomes the parametric equation of the line segment. Okay, so with this in hand, now let me go to this inequality. Okay, so here on the right side of the inequality, we have a function f of line segment between u and v. So this is a parametric equation of the line segment joining u and v. Okay, so in case of a single variable function, so u and v in this case will be 2 points on the horizontal axis. Okay, so the line segment between u and v will indicate this line segment. Okay, so by substituting one number for theta, we can represent any point on this line segment. Okay, so what is the right-hand side? That is a function's value at some point on the line segment between u and v. Okay? So that corresponds to this graph, the function's graph. Okay? So if we compare this with the line segment AC, okay, that is going to be the left-hand side. Okay? So we have f of u and f of v, so two different points. Now these two different points appear on the vertical axis. Okay, so f of u, that is going to be y coordinate of this point A, right? And f of v, so function's value at point V, so the y coordinate of this point is C. So theta of fu plus 1 minus theta of fv, so this expression is nothing but the parametric equation of the line segment between f of u and f of v. Okay? So in other words, that is a y coordinate of one point on this line segment. Okay, so suppose, so think of theta equal to 1/2. Okay, then we have a midpoint of this line segment, and that is going to be a y coordinate of the midpoint of line segment AC. Okay, so we can call this expression on the left the line segment AC. Okay, so when function is bent downward like this, if we compare these two quantities, this is a typo. It should be inequality should be reversed. Okay, we can easily see that function's graph is above the line segment AC. Function's graph is above the line segment. Okay, and in case of a convex function, the inequality will be reversed. So now the line segment is above the function's graph. So think about the convex function. So we have x-axis and y-axis. We have function now bent upward. Okay. Choose any 2 points on the horizontal axis, u and v. So now y coordinate of this point is going to be f of u, and f of v is y coordinate of this point. Okay, so now let me join these 2 points with a line segment. So you can easily check, the case is opposite, right? So now the line segment is above the graph of the function. So the parametric equation of this line segment is theta f of u plus 1 minus theta f of v. Okay. So originally this is the line segment, this one. Okay. But once again, one value on this line segment will be equal to y coordinate of some point on this line segment. Okay. So that determines the height of this line segment, and we compare the height of this line segment and the graph of this function, the height of this graph. Okay. And then we can see that line segment is above the graph of the function. So that means this quantity is now higher than, larger than the function's value, over this interval. Okay. All right, so that is a formal definition of the convex function. And this one is the this one is the definition of concave function. So it is readily extended to any function, no matter what the dimension is. So here we have a three-dimensional space. Now the function depends on two variables. Okay? Regardless, we can choose 2 points in the domain, u and v, okay? And then connecting them with the line segment. Okay? And then we evaluate the function over this line segment. That is this black curve. Right? And then the quantity on the left hand side that will indicate this dotted line connecting M and N, right? Because f of u will be the height of this point M, okay, in this three-dimensional space, and f of v the height of this point N. Okay? So the line segment, this dotted line segment connecting M and N, is captured by this linear combination. Okay, so in case of a concave function, the graph of the function is always above the line segment. Okay, so the concave function can be characterized by this property. So another way to define concave function is using derivative. So whenever a function is differentiable, then we can define concave function this way with this inequality. So think about the f of v minus f of u. Okay? So that is that difference is going to be the length of this line segment. Okay? So the line segment is C and D, the length of this line segment. Okay? And f prime u, okay, that is the instantaneous slope of the tangent line. So the slope of this line A and B. Okay, the slope of this line segment. Okay, and then we multiply by v minus u. Okay, v minus u is a change in x. Okay? So if we multiply the slope of the tangent line by the change in x, we obtain the change in y on that interval. Okay, so that is going to be line segment BD. Okay? So this is a line segment BD, and f3 of minus f of u, that will be line segment CD. Okay, so we can easily see that BD is longer than CD. Okay, so we have this inequality. All right, and from this, we can see the relationship between the second derivative, the sign of the second derivative, and concave function. So we defined concave function in terms of the negative sign of the second derivative. So the way to see that from this inequality is, let me divide both sides by v minus u, because v is higher than u. Okay, v is a larger number than u. So dividing by v minus u does not reverse the inequality. Okay, so we still have this is smaller than f prime of u. Okay, now let me relabel u by v minus h. V minus h. Okay, so h is some number larger than 0. Okay, so that stands for the gap between v and u. Because v is a larger number, so some v minus some constant h is going to be u. Right? Then I can rewrite this. So I can rewrite this fraction as f of v minus f of v minus h. And the bottom is going to be h. Right? And then take the limit as h goes to 0. Okay? Because the right side is just f prime of u, so that is independent of h. So we still have this inequality, but the left-hand side, as h goes to 0, it converges to derivative of, so the derivative of f at point 3. Okay, so we have f prime of v is smaller than f prime of u. Okay, so the first derivative is decreasing in case of concave function. Okay, so the derivative, it turns out to be decreasing. That means the second derivative is negative. So that illustrates the relationship between the sign of the derivative and the concave function. Okay. In case of a convex function, you have the so reversed inequality. Okay. So now the derivative is increasing, so the second derivative is positive. All right. So its counterpart in multivariable case is the next. So if function depends on several variables, so here is the formal definition. And what is some easy criterion to see whether a given function is convex or concave? That bears on this Hessian matrix. Okay, so if the Hessian matrix is a negative definite, then function is concave. And if the Hessian matrix is a positive definite, then the function is convex. Okay. So in case of a two-variable function, if we have this kind of graph, then the Hessian matrix is going to be negative definite. So negative definite, and in this convex function, the Hessian matrix is going to be positive definite. Okay. All right. So here is a formal definition of a concavity, and there is a one simple criterion that tells us whether a given function is concave and convex. Okay. So now we are going to use this criterion to determine whether the following function is concave or convex. Okay. So we have a function depending on two variables, x and y. Okay, so we can easily find we can easily construct the Hessian matrix of this function. So f sub x, let me first start with first order partial derivative. So that is 4x minus y. And f sub y is negative x plus 2y. So from each, I can compute the second order partial derivatives f sub yx, but that is going to be equal to f sub xy by Young's theorem. So we don't have to compute this. And finally, f sub yy. So f sub xx is 4, xy, that is a negative 1. So f sub yx is also negative 1. F sub yy becomes 2. So the Hessian matrix is 4, negative 1, and negative 1 and 2. Okay. So using the principal minor, we can tell, so we can determine the sign definiteness of this Hessian matrix. So the first entry, so the first reading principal minor is positive. And the second, the determinant of this 2 by 2, a minus negative 1 squared, that is positive. Okay, so the two principal minors are positive, so this Hessian matrix is a positive definite. Okay, so this function is convex. And we can use the eigenvalue test as well. So, given this Hessian matrix, now we can compute the characteristic equation. So we can derive the characteristic equation first. So a minus lambda I. So with this Hessian matrix, so instead of a, let me use h for Hessian matrix. Then coefficient matrix is going to be 4 minus lambda, negative 1. and -1 and 2 minus lambda. Okay, so the characteristic equation is we compute the determinant -1 squared and set it equal to 0. Okay, then lambda squared minus 6 lambda plus 7 plus 7 plus 7. Okay, so unfortunately this is not factorable, but using the quadratic formula we can find the solution to this equation. So lambda is 6 plus minus square root of 36 minus 4 times 1 times 7 and divided by 2. Okay, so that is 6 plus minus square root of 36 minus 28, that is a square root of 8. So that is either 6 plus square root of 8 divided by 2, that is positive, and 6 minus square root of 8 divided by 2, that is also positive. So the two eigenvalues turn out to be positive. So we can make sure this Hessian matrix is positive definite. Okay. All right. So now let me summarize the chapter 11. Okay. So in this chapter, the punchline is how to maximize or minimize multivariate function. Okay. So in case of two variable function, for the condition for local max is going to be the first of the condition is, if the two partial derivatives must be 0. So, if we have a local max at point A comma B, then f sub x a comma b and f sub y a comma b, both of them should be equal to 0. Yeah. And the second order condition can be stated in different ways. So if the function has a local max at this point, then the Hessian matrix must be negative definite. Okay. Equivalently, all eigenvalues of this Hessian matrix evaluated at a comma b at this critical point is negative. Okay. And then, in other words, the function is concave. Okay. So these 3 or 4 statements are equivalent. Okay. Likewise, if the function obtains a local minimum at this critical point, then the Hessian matrix evaluated at point A comma B should be positive definite. Equivalently, all eigenvalues of this Hessian matrix are positive. Or equivalently, the function is convex at point A comma B. Okay. So I think this is almost everything about chapter 11. So I hope you guys enjoyed this video. And if you guys have any questions about the optimization, don't hesitate to send me an email. Okay. All right, then wish you guys have a great weekend. Then I'll see you in the next video.